Let me share this screen. Maybe, there we go. Alright, so when we complete this lesson, we should be able to do the following: identify common zoning systems and describe the basic approach to troubleshooting. Describe common zoning system components. Describe the sequence of operation for common zoning systems. Describe the basic approach to troubleshooting common zoning systems. Alright, so with the zoning system on a residential system especially, but in general, you will have separate trunks that come off of your supply plenum that have zone dampers in them. Usually the return stays common, so there's nothing that splits up zones on the return side. That's because when you zone the system, like say this zone damper 1 is closed, but the zone damper 2 is open, you're going to restrict the airflow. So there's two ways to approach that problem. All right. Because as we all know, if you start dropping CFM, you're going to adversely affect the airflow in the system. You're going to adversely affect the air conditioning, especially, but the heating as well. So what you do is, and they're not showing here, which hopefully we'll get to, but if not, I'll discuss it more, is you put a bypass between the supply and return to keep the system able to keep circulating the same amount of CFMs. But a lot of it gets bypassed back through the system instead of going to the house. Alright. The other thing that you'll have here, besides the bypass that they don't show, is a discharge air sensor. And if the discharge air gets too hot or too cold, depending on whether or not you're in heating or in cooling, it'll shut off the system until the discharge air temperature drops below a certain point, and then it'll allow the system to kick back on. That way you don't overheat or freeze the coil, because both of those things can be a major issue. So zone dampers on the supply side that open and close, alright, they're just dampers operated by a solenoid, which hopefully most of you guys are familiar with, whether you see them in fire smoke dampers or you see them on VAV systems or whatever the case may be. It's the exact same thing, just usually a 24-volt actuator that opens and closes a damper. Discharge air sensor, a zone control panel, which is everything is basically going to be controlled from that zone panel. Thermostats for every zone, and then a transformer for the zone control panel. So it's pretty simple overall. The hard part about zoning is balancing it right, especially that bypass air. They've got newer zone dampers that allow you to set a specific static pressure to go at, but the older ones were balanced by a weight, so the weight would counteract the air so that you would maintain a static. And the idea was to try and keep the system running around, a 1/2 inch to 8 inch water column static pressure maximum. And those can be pretty tricky to dial in. It's kind of a lost art for the most part, but newer systems, you have better ways around that. The other way you can approach it, besides having a bypass, is to have a communicating system with a variable speed fan, in which case the zoning system operates a lot more like a commercial VAV system. So a commercial VAV system, all your modern ones anyway, the older ones had bypass dampers and everything just like a residential system did. But a commercial VAV system, you modulate the airflow through a VFD on the supply fan. With the residential one, it'll be an electronically controlled variable speed fan. And as the zones close, that they communicate back to the system that they are closing, so that the system will drop airflow and drop the capacity of the outdoor unit. So those are really the best options when it comes to residential zoning. But but it's still only, I think, a few manufacturers really offer that option completely. It's probably more by now, but I'm more familiar with Carrier's version of zoning with their Infinity systems. When it comes to residential, um, I think Train or Ream have to have something similar by now, but I've never worked on them. Um, but that approach is very good. Just my 2 cents on zoning when it comes to residential is that on residential zoning, it's generally a solution for engineering problem. I'm trying to think of a better way to put it, but basically, zoning really shouldn't be required in most residential formats unless you have a very large house, in which case zoning may help. But if you got a very large house, you should probably be zoned by systems more than you should be zoned by zone dampers. But if duct is designed real well, you really shouldn't have to zone different areas of a house. Now, that doesn't mean it doesn't have its place, but in my mind, it's more of a band-aid to a duct design issue. But the thing is those duct design issues are extremely common, so it's not the worst solution for that problem. But just keep that in mind. There's a lot of other things you need to take into account if you're designing a zoning system, but as far as working on them, it's not very complicated. It's basically just adding a bunch of automatically operated balancing dampers to the system for the most part that either open or close, and most of them have a minimum open position so that they're supplying some amount of air even if they're closed. It's just very small. Alright, so older zoning systems as well as some new ones, only the master thermostat provides mode switching capability, and that is very common even on the newer ones. Obviously, you can't have one thermostat calling for cooling and one calling for heating. This is not a VRF system, right? So the system has to be running in heating or cooling at any given time. So older systems, you're going to have one thermostat that allows the system to switch between heat and cool. On newer systems, other systems, if they're calling for heating during cooling, they might allow the system to switch at a certain point. But if you've got one zone calling for heating while another zone's calling for cooling, you have a setup issue. You really shouldn't be running into that problem. It might occur on weird days, but for the most part, you're really poorly designed if that's occurring on a regular basis in something as small as a residential house. Again, larger houses may be the exception, but we're talking about pretty large houses, like I would say in the realm of 10,000 square foot or more at a minimum before you should be having those kinds of issues. Zone dampers are usually powered closed rather than powered open. There's an obvious reason for this, right? You want the zone to be powered closed because if you have no power, you want that damper to automatically open. It would be very bad if just the zones lost power and everything closed and your system was running for some reason, right? So especially considering these are usually controlled by a separate transformer, if that transformer goes, you want the fail position to be open on a zoning system. You don't want the fail position on a zoning system to have the dampers all closed. Alright, so these are normally normally open dampers. The dampers are normally open. And you'll want to remember that. Zone dampers are usually powered closed, not powered open. A zone damper diffuser serving a single room can solve overheating or overcooling problems. And this is true, like I said. If the system's designed well and balanced well, you should really not need zone dampers in 90 to 95% of homes. But if you do have issues with duct design, or it's not well balanced and there's no way to remedy that issue, zoning is cheaper than redoing the whole duct system. And part of the reason why I emphasize this is that you don't want people to use zoning dampers, a zoning system, as a means of not cooling or heating unoccupied areas of the house. In other words, the goal of a zoning system isn't so that you can set all the bedrooms at 80 degrees during the summer since nobody's in their bedroom, because you're usually going to waste more energy overcoming that heat difference between different spaces of the house than you are going to save energy by not cooling or heating certain portions of the house. So in other words, on a zoning system, pretty much all the thermostats should be set close to the same temperature, within a couple degrees. It's not there to, create an occupied and unoccupied mode for different portions of the house. That is not a good use of zoning. A lot of people seem to think that that's a good idea to do on a house that is zoned, and in general, that is not a good idea. All right, bypass dampers must be able to modulate their position to accommodate system needs. So these are your old style ones right here. The one on the right, that is your old style zone damper. Bypass damper that has a weight on it, and you move this weight up and down on this rod, and that gives it a different amount of force, right, that it applies to this lever that's connected to the damper on the inside. So this weight, the air has to overcome this weight to bypass the air. So as the static increases, the pressure of the air increases. When zones close, it will be more able to force this damper open, and as the more zones open and the pressure in there decreases, this damper will tend to close. And ideally, this should completely close if the whole system is calling, and open just enough to maintain a maximum static pressure when not the smallest zone, because you got to have a minimum airflow. Even on zoning, you can only zone so much, but basically at its minimum amount of airflow. At the minimum amount of airflow in the zoning system, you want this thing to open as little as possible, but just enough so that you're not creating too much static pressure in the system, because that will create an issue where you've got basically no airflow. Once the fan deadheads, once there's so much static pressure that the fan can't really move air, that fan curve hits a point where it just basically your airflow drops off a cliff. Bonus question. I want you guys to think about, maybe type it in the chat or text me your answer. If you've got, say you had a damper right off the top of an air handler, okay? If you had a damper right off the top of an air handler so that it could close or open all the air flow in the system. If you close that damper and the system cannot move air through the supply trunk at all, so it's completely closed, would that system draw more or less amperage than the nameplate amperage of the motor? So in other words, if that was a 2 amp motor, would it start drawing 4 amps if you close that damper all the way? Or would it draw 1 amp or less than an amp if you closed it all the way? Bonus question. If you guys do hydronics, hopefully you know the answer to that. But more? Alright, we'll talk about that in a couple minutes. Just swish it around your head for a minute. Alright, and then this is the newer stuff, the motorized or modulating bypass damper. The neatest ones I've seen so far, and well, no, I shouldn't say the neatest. The most user-friendly ones I've seen so far is Honeywell makes one where you can just set the static. So you can just set the static at 0.5 and it'll modulate to maintain a 0.5 static. I'm sure they have electronic ones. I haven't had the pleasure of putting any of those in, but obviously that is an even more sophisticated solution to this bypass damper issue. I haven't worked on very many barometric bypass dampers, but from everything I read and studied on residential zoning systems, these barometric bypasses, there's basically no hard and fast rules to get this right. You've got to get it close to where it should be, and then you got to you got to kind of just dial it in by feel. It can be very hard to get these barometric bypass dampers set up just right, to where you're not overcycling the system, but you're not creating too much static there either. Alright, so there's two ways of dealing with this. Your older commercial solution with a bypass would be a dump zone. So a dump zone in a commercial building would be like a mechanical room or something, somewhere where nobody cared if the temperature was really regulated that well. So you'd go to an unoccupied space basically, and you'd bypass into a dump zone, so that if you had too many zones that close, if too many zones closed, so you needed to bypass some air, you just dump all the extra airflow into that room. I have seen a couple of those buildings, older buildings in like Fort Belvoir and stuff like that. I've seen buildings with dump zones in them, and it's kind of neat. That's what they did before VFDs were reliable or plentiful. I've never seen a house that had a dump zone. Obviously, obviously they're saying put a dump zone in a basement. I guess you could, but again, most modern houses are going to have at least somewhat finished basements. There's no real good place for a dump zone in most houses, but it is one way to handle the issue. The other way to handle the issue is, like I was talking about before, your direct return bypass. So as you can see, your supply air comes out of the unit, goes to the space, to all your zones, and then you've got the bypass damper there that will just short cycle from supply to return. Now this still sucks, alright? Bypassing air like this, obviously, say you got a furnace, running full tilt. It's a single stage furnace or something like that. That furnace is normally going to have about 120 degree air coming out of it, right? 120, 130 degree air. And if you're dumping 130 degree air back into the return, depending on how much you're pushing, you're going to quickly have 150, 160, 170 degree air, and that is not good for a furnace. So that's why you have the discharge air sensor to cut that system off once it starts exceeding what you really want that air to be, and you're going to want to set it to whatever the furnace manufacturer's maximum heat rise is. And then same thing in cooling. If you're bypassing 55 degree air into the return, and you've only got one zone calling and it's only pushing about half the CFM, you'll quickly get to the point where you start freezing the coil and you've got very little superheat. Very little superheat back to the compressor is bad, right? So you can quickly cause a lot of issues. So the discharge air sensor is an extremely important part of this whole bypass arrangement, because you need to control the temperatures in that system pretty carefully to make sure that the zoning system doesn't cause more problems than it creates solutions. Zoning control panels are generally pretty simple. This is a pretty good diagram of one. Very similar to what you're going to see out in the real world, no matter who you buy it from. You'll have your discharge air sensor connection, HVAC unit terminals, so this is where all the signals go to the HVAC system. Alright, and then you'll have your other thermostats, your zone thermostat and a zone damper, another zone thermostat, another zone damper, another zone thermostat, another zone damper, so on and so forth. And however many zones it'll connect is what you'll have there. Sometimes all the thermostat connections are on one side and all the dampers are on another. A lot of times it's set up just like this. And you'll have a common for the damper, and then powered closed and power open terminals. Again, generally you're going to be using those power closed terminals. So you'll have common, power closed going to your dampers, and then all your thermostat connections go back to here. And on most modern systems, basically this zone control is what's going to determine whether or not the system goes into heating or cooling, which is why you have all the connections here. So yeah, then you'll have LEDs telling you whether or not the zones are open or closed, and LEDs telling you what condition the system is in, whether it's running and heating, running and cooling, whatever. And then you'll also have either programming, or you'll have dip switches to set different settings, like this one is showing dip switches to change the high limit setting, which again is you're gonna want to match the manufacturer's instructions for a furnace on that. And then you'll often have test terminals and stuff like that to test the individual dampers and things like that, so you can make sure they all operate. And then this one, they're showing a purge switch, which just keeps the system running a little bit longer after the last zone is satisfied, to try and, get all the rest of the heat out of the system, or all the cold out of the system. Note the lack of zone damper and thermostat wiring terminals. What are they talking about? I guess this is a fancier one, that the zone dampers connect probably by a communications system or something. I've never seen that, like I said, outside of maybe the Infinities. It's been a while since I set up one of their panels, so I can't remember all the panel connections. But this one has a display module to program everything instead of having all your individual outputs. If you're trying to figure out whether the zone damper is open or closed, there's usually some indicator here. So like on this one, right here on this side, it's just like a Belimo actuator. So this thing moves, and that tells you what position it's in. One side will be fully open, one side will be fully closed. If you're ever working on one, it's very good, very, very good practice, okay, to mark this shaft with a black mark indicating the position of the damper, because sometimes these actuators slip depending on their design. The actuator can slip on the shaft, and even though it feels like it, or it looks like the actuator's in one position, the damper's in a completely different position. So if you're ever setting one of these up, or you're working on a VAV with a shaft where you can see the actuator or whatever, stick a little black mark that's exactly in the position of the damper, so that when someone looks at that shaft, they know what position that damper is in, because that can make troubleshooting way simpler. I mean, it doesn't take you much effort usually to disconnect the actuator from the shaft and feel the damper for the full closed and full open position, but it's infinitely simpler if somebody was smart enough to mark it on it, and most guys are. Most guys will go through the trouble, if the marking's not already on the shaft, to mark that shaft for the damper position to tell you what it's in. And then zone controls, a lot of times they'll show a light, but this light again only tells you whether the actuator's open or closed. It rarely tells you if the system's actually open, or like the damper's actually open or closed. It just knows what position the actuator should be in. So if the damper slips on the shaft, or the actuator slips on the shaft, then even though the actuator says it's closed, the damper could be open. And there's very few ways to prove that. You can do it with an end switch, but the way a lot of end switches are made, those can slip and give you a false security of what position that damper is in. So a good old black Sharpie is usually the best way to tell for sure what position it's in on installation, or on a service where you have to disconnect it and set it back. Alright, zone and mode priority. Heating and cooling modes can both be called upon from various zones at any time. The zone calling first takes priority. Once the first zone reaches the desired temperature, a purge period begins before the call for a different mode can be answered. However, without sharing capabilities, the first zone could dominate system control for a very long period of time, which it should. Again, zoning is not an excuse to run heating and cooling at the same time to maintain a very tight temperature window in a house. That's not the way it should be used anyway. If the zoning system is capable of sharing, the runtime for a given mode is typically limited. Once the time period is over, the system will change modes to satisfy the other demand, regardless of whether the first call was completely satisfied. The most common method for controlling the second and or third stages of heating and cooling is based upon the time the zone has been calling for conditioned air. If it is not satisfied by the first stage in a preset period of time, the second or third stages will be enabled, and that could be 10 minutes, could be 15 minutes, could be 5 minutes. It depends on how many stages you are and how you're set up. Whereas like a commercial VAV system, right? A commercial VAV system, instead of setting it up based on preset period of times, you'll set it up based on discharge air, so that if you're only calling for part of the building, one compressor will maintain 55-degree air. But if the whole building is calling, it might take 3 or 4 compressors to maintain 55-degree air, or multiple stages, however it's set up, if it's unloaders and things like that. But commercial systems, it's generally the temperature that stages it. Residential systems, it's usually as simple as time. It doesn't try to maintain a set discharge air temperature, although I want to say the newer ones will stage cooling. If you've got like a 2-stage system, I think it can try and maintain 55, but I've never set one up that was in that position, so I could be completely wrong. Each zone of advanced systems can often be programmed for a different period of time before the second stage is enabled. Advanced systems may also offer programming that requires a minimum number of zones to be calling for heating and cooling before a second or third stage starts. And obviously that would be because the more CFM you're pushing, the more likely you are to have a higher delta T. Is that right? No, a lower delta T, right? You'll have a lower delta T if a lot of zones are calling, but even if only one zone's calling, one stage can usually maintain a very warm or very cold air temperature to the space. Remember that these are cycling limits as opposed to safety limits that lock out the equipment. They are not intended to replace any existing system safety. Yeah, the discharge temperature sensor is not there to provide a safety for the compressor or anything else. It is just there to set limits, and what you're trying to do is keep the system from cycling too much, because anything, right, whether it be a motor, a compressor, which has a motor in it, right, a gas furnace, the actual burners, anything cycling on and off and on and off is generally bad. Anything you can do to try and keep a system from cycling too much is a good thing, whether you be working on a well pump or an air conditioner. You want that thing to run as long as possible generally. So if you can do that, that is a good thing. Panel indicator lights can provide status information for all parts of the system. We talked about that. Many people use switches for many panels use switches for some basic options. Again, testing, there usually be a test switch, stick it in a test mode. Basic system settings, things of that nature, is often dip switches. Determine if the thermostat is faulty by measuring voltage at the panel terminals. I mean, just like troubleshooting anything else. If you're having issues with operation, you want to make sure all the signals you think are there are there. Note that this terminal board is marked to show which input opens and closes a 3-wire damper. Again, if you got common, powered open, and powered closed terminals, 3-wire damper utilizes all 3 of those terminals. A 2-wire damper uses only 2. So a lot of times they're powered closed, spring open, right? A spring makes it open, but a power terminal forces the actuator closed. If you have a 3-wire damper, the actuator moves both positions, so you'll have to send powered open to open it and powered closed to close it. Yeah. So, we'll talk about these, then we'll talk about that bonus question I asked you. What do you expect to happen if a 2-wire damper motor suddenly loses power while it's moving? Well, it should spring open, right? Since 2-wire dampers are normally powered closed, the spring will reopen the damper on a loss of power. What do you expect to happen if a 3-wire damper motor suddenly loses power while it is moving? Well, it needs power to move in both positions, right? So it'll probably get stuck in the position it's in. If 3-wire dampers are powered in both directions, the damper will typically stop at its present position. Oh, is that it? Those are the only two questions? All right. So there's that. Now, back to the question I asked you. Let's go ahead and look at a picture just for funsies anyway. So, here's what happens, okay? A fan has a curve. Well, no, I'm not going to bother. I'm not going to bother trying to pull it up, but try and pull up a fan curve one day. Just Google for fan curve online and you'll see one. But typically what happens with a fan curve is if you're looking at power usage, right? The power usage, as the pressure the fan has to work against is low, the fan is down here, right? Can you guys see my mouse cursor? Yeah, I think so. Anyway, as it moves up, you draw more power, right? As the static pressure on it increases, the fan keeps utilizing more power, right? So as you have to work against more pressure, feet of head with a pump, inches of water column with a fan, that the power usage goes up as that motor continually has to work harder to do the same amount of work, right? To move the same CFM, to maintain the same RPM, whatever the case is. Well, once you get to a point where the pressure and the pressure exceeds what the fan is designed for, right? Because typically this is going to be the upper limit of the design. So as the pressure or the head pressure on a pump motor, or the static pressure in the HVAC system for most residential systems between 0.8 and 1 inch of water column. Once you start hitting that static pressure, the fan can no longer do any more work, right? That's the most work it can do. You've exceeded what it is capable of. And once you hit that kind of that soft peak, everything drops off. Okay, so you've got kind of a slow climb. And then the next thing you know, everything starts to drop off. Airflow drops off and power usage drops off. That's because if you've got a motor, a pump motor or a fan, and you're deadheading it, right? It has nowhere to move that air. It has nowhere to pump that water. It only stays, all the water is staying in the impeller, or all the air is staying in that squirrel cage. It can't do any work. There's nowhere for it to go, so it just freewheels. Now there's other problems associated with it, right? Especially the larger the motor gets, the more dangerous this situation is. But in general, on small fractional horsepower motors, whether they be in a pump system or in a air handler, deadheading that motor causes no problems. It can't do any work, so it just freewheels. So your amperage actually drops, and almost everybody invariably thinks that as the static pressure goes up, or as you deadhead something, the amperage will rise. Well, it will rise to a certain point, but if it's completely closed, that motor cannot do any work. There's nothing to move, so it goes whatever the amp draw is for it doing nothing. So basically the close to the same amp draw as if everything's just wide open and it's just sitting there on the table spinning. That's the amp draw that you're going to pull, which is usually much lower than the rated amperage. Okay, so now on really small motors, no matter what, it's very close to the rated amperage. The smaller the motor is, the more it tends to draw the same amperage all the time. But overall, the point is if you completely close the discharge side of a circulation pump, or you completely close the airflow on an air handler, your amperage will drop. It'll go basically all the way down, as low as it'll go. That's because it can't do any work at that point. Now, on large motors, that can be very dangerous because they're not made to just freewheel like that. They need to do work, right? But on small motors, it's perfectly fine to just completely cut that off, which is why we always balance. It's always best, especially with water, to balance on the supply side of the system, never balance on the return side of the system, because you can cause a lot of problems if it's not getting air or water to move. You don't really create any problems if you close off how much air or water you're going to move. So especially with circulation pumps, but even with air fans, remember you always balance on the supply side. You don't balance on the return side. The only balancing you should do on the return side is to maintain minimum CFM drawing from a space. You should never close off that side to lower the amount of airflow or water that you're moving in a system. So hopefully that explained it well. Alright. Alright, any questions so far on anything?
Good so far. So far, so good.
Alright. Alright, now we're going to go over some other stuff. Let me make sure. Oh no, I still have to share the screen with you guys anyway. Okay, good. So I've got it in OBS. Now I just need to share the screen. Alright, when you've completed this session, you should be able to do the following. Identify common zoning systems and describe the basic approach to troubleshooting. Describe common VVT system zoning components. Describe the operating characteristics of a VVT control system. Identify ductless and variable refrigerant flow systems and describe the basic approach to troubleshooting those. And identify and describe the operation of ductless split system equipment. Alright, VVT. You have variable volume, right? Variable volume system. Rooftop heating cooling unit. Bypass damper to ceiling plenum or return duct. So this would be a dump zone into the ceiling plenum or return duct. Ceiling plenum or return duct. VVT is like, I can't even remember what it stands for. Do they tell us in here? I can't remember exactly what it stands for, but VVT is like 1970s, 1980s zoning systems, okay? You were talking about older commercial controls, and you just don't see them very often. Most of the VVT systems have all been retrofitted to be standard VAVs at this point. But a lot of these principles are very similar, so it doesn't hurt to go over it. Alright, so you have a rooftop heating cooling unit. Sometimes it's cooling only on an actual VAV system. A lot of times on smaller systems that would have a VVT system, it is heating and cooling. So this is basically just to control like separate offices and things like that when it comes to a VVT system. So you have return air. A lot of times it's a plenum meaning that the air above the ceiling is your return air to the unit. So your grill just transfers the room air to the ceiling above the room, and that air gets sucked through the ceiling to the unit. So that's your most common commercial return arrangement. Otherwise it's ducted, all returns like normal, right? So return air grill there, supply diffuser, supply ducts, right? Zone dampers, these all these right here, your individual zones, similar to your VAVs, right? Zone damper master controller and master zone controller, the controls that's going to be basically manufacturer specific but set up very similar to a residential zoning system. Zone controllers, communication bus where they all communicate back to the master zone controller. Rooftop unit controller will be in the rooftop unit itself. Generally, it's just a standard rooftop. May have a single or a variable speed fan in it, one or the other, but the older ones obviously were still single speed fans. And then bypass damper and controller. And this was another way to do a dump zone. I was talking about how they used a mechanical room. You can dump zone into the plenum as well, but obviously that's not much different than just doing a straight bypass to the return, right? You're still dumping air right into the return air. So it creates a little less headache than actually connecting the bypass duct to the return duct, but not that much. It depends on how big this building is and how big that plenum is. It could have a small effect on the temperature in that plenum. It could have a very large effect on the temperature of that plenum. And obviously a large effect on that temperature is going to have a large effect on the return going to the unit still. So you still may have issues with discharge temperatures. Unlike a common zone damper, VVT controllers must collect and report information. So they collect information on the static pressure in the system or the temperature of the outlet and all that nice neat stuff, and they send it back to the master zone controller, usually through BACnet, which is still a common way of communicating in commercial systems. Older primary zone controllers, also known as master thermostats, they provide basic information such as time of day and operating mode to other thermostats. The master also gathers demand information and determines what operating mode will be selected. The master thermostat also maintains its own zone conditions. Newer primary zone controllers, no master thermostat is needed. Computer software handles the supervisory tasks through a network. Operating information is stored in each zone controller, enabling it to operate regardless of whether or not the computer is online. And that's very common too if you're talking about a commercial system, VVT, VAV systems, whatever it is. If the zone loses communication, generally it's going to stay operating in the position it was when it shut down. So you will usually maintain system operation even if there's no communication until the temperatures get way different or out of whack and it's operating in the wrong mode or whatever. Communication bus to previous device, 3-wire conductors wire to a shield. Thermostat block connection wiring, control wiring, 5-conductor with shield, damper actuators, ribbon connectors, terminal board, zone controller. It is common for a lot of commercial systems, including some VRF systems, to require shielded wire. It's very important if you're working with shielded wire, which shielded wire has like an aluminum shield inside the casing. So you have the plastic outside the wire, then you'll have an aluminum shield inside that's meant to shield the wire from interference, and then your wires inside, and you'll usually have like a ground wire that runs along the inside of that shield. And the purpose of that is to ground the shielding somewhere so that the interference that gets basically picked up by the aluminum shield, right, gets carried to ground. And that's to try and prevent radio frequency interferences, electronic interferences from electronic equipment, things of that nature. If you are dealing with a system that a wiring that has a shield, or your system requires the wiring to be shielded, it is extremely important that you follow the instructions that the manufacturer gives you for shielding. In general, the rule of thumb is that you should only shield one side of the wire, because you don't want to create a ground loop, because that can create interference on its own. But some manufacturers want you to ground both sides of the shielded wire. So always follow their instructions. So if you have a problem, you can blame it on the manufacturer's instructions and not your installation. In general, the issues you would have with shielding both ends aren't common enough or common at all in HVAC systems to where it's a problem. It's just a nice thing to note. Communication. Basically, they all communicate back with each other. All this stuff is going to communicate together, okay? You're going to have the zone system communicating with your damper, or the zones communicating with your damper back to your main zone controller, the main zone controller communicating with your bypass damper and your rooftop unit. The volume of airflow through the damper is completely dependent on system pressure. The damper cannot control the actual volume. This is, I don't know. I don't know if I like that being stated that way, because on most systems that you're going to encounter, yeah, the damper, the amount of flow is going to be dependent on the system pressure. And most systems are going to maintain a specific pressure because the system is going to be set to run at 1 inch of water column or 2 inch of water column or 5 inches of water column or whatever the case may be. So often you have a variable speed fan that will maintain a particular static pressure. But if you got like an older system like this with a dump zone, the system may change pressures. But at the same time, often these things have air pressure sensors in them, right? They have basically little pitot tube arrays in there, and those will tell the zone what the static pressure is, and then the damper can further modulate to maintain volume. But if your pressure drops so far, then the damper is not going to be able to open anymore to provide more airflow, or if it gets really super high, no matter what that damper does, it's going to be hard for it to shut off the air, especially because a lot of them won't shut off to completely 100%. Zone votes determine the system reaction. So each zone gets 1 vote for heating or cooling. A vote is based on an actual call for one or the other. No call equals no vote. The majority of votes determines the mode. Other parameters can be sometimes added, though. A minimum number of votes required to change the mode can be programmed into the system. Additional stages of cooling come on if the demand grows or is unsatisfied after a period of time. When heat is called for, when the system is in the cooling mode, the zone's damper goes to the minimum position if it is not already there. If the majority of zones begin to ask for heat, the system changes modes and begins to satisfy their demands. Zones not needing heat move their dampers to the minimum position. Heating mode ends when the average heating demand falls below a preset minimum. Not enough zones need heat. When a greater average cooling demand occurs, or when cooling demands have gone unanswered for a preset period of time. And this is kind of special to commercial systems, right? In a lot of commercial buildings, you need cooling almost year-round, right? Especially larger buildings. The larger the footprint, the more likely you are to have this issue, because you can only get heat loss to the outside, right? You only lose your heat to the outside air, but you can gain heat from people, equipment, lighting, electronics, whatever. So you are more likely to gain heat in a building than you are to lose heat from the building. So, in a commercial VAV system, for instance, a lot of times the only zones that have heat are the zones that are actually on an outside wall or ceiling, right? And then all the zones on the interior will be cooling only, because they only experience heat gain, they don't experience heat loss. So on a VVT system, especially if it's a larger one, it could be 20 degrees outside and you've got a lot of zones calling for cooling. So heating is usually going to take the back seat to cooling. Ductless splits. Alright, so talking ductless splits, we talked VRF a little bit the last class. But talking ductless split systems, there's not a lot that's super special about a ductless split. It's a basic split system. It looks a little different, but it operates very similar to any other refrigeration system, right? As a matter of fact, it operates pretty damn close to how a, commercial walk-in cooler operates. It's basically a ductless split, right? And older ductless splits were just that, split systems with, basically a unit with no ductwork attached to it, no big deal. The thing that makes ductless splits kind of special is their control system and how efficient they are. Most of their efficiency comes from the fact that there's no ductwork, right? We don't have to have a big powerful fan to move 2000 CFM across, you know, zero point 0.6 inches of water column so that we can heat a whole large area. Instead, we'll have a multiple or one mini split system or ductless split system that the fan only has to be able to push a certain amount of CFM through just this coil. The coil is basically the only resistance it has to work against that, and usually very air-friendly filter, right? A filter that air goes through quite readily. So a lot of their efficiency is just derived from that. Remember, when you're talking a ducted system, you can have 25, 30%, sometimes even more losses just in the duct. So 25, if you got ducts in an attic, then 25% or more of the heat or cooling you create, the heat you produce or the heat you remove, is going to be lost just in the ductwork. So that system that's in that air handler that's in the attic connected to ducts that are in the attic, if that's a 2-ton system, the load for the space is probably only about 1.5 tons. A half of that ton is lost in the ductwork. So that's a pretty large system loss, right? Those are very big system losses, which is why it's so important to install ductwork very well, very tight, and insulated. But ductless splits don't have that issue, so that's why while our most efficient ducted system right now, talking residential, right, our most efficient ducted systems are in the 20 SEER range. Our most efficient mini split or ductless systems are closer to 28, or I think they even hit 30 something now. So all that SEER, all that energy efficiency is because you don't have duct losses. The biggest difference that people notice on ductless splits right out of the gate is that both lines are insulated. That is because depending on the design of the system, oftentimes your metering device is outside, not inside. So that liquid line is actually after the metering device to the indoor unit. So that is why that needs to be insulated most of the time. Other systems are not made up like that, but even still, because of the temperatures the system experiences, a lot of times you need that second line to be insulated. But yeah, that's the biggest deal. Both sides of your line set are insulated on it. That's one of the first things guys notice. Everything else is pretty simple, except for that a lot of times they're proprietary controls and it's a communicating system. So obviously there's a lot less troubleshooting you can do on a ductless split without knowing the manufacturer's instructions on troubleshooting it. Outdoor unit also houses the expansion device. Variable speed compressors are fairly common. That's where obviously another big jump in your efficiency comes from, is almost every mini split these days is an inverter compressor. Mounting this unit high on the wall creates more efficient air movement. They are the most common style. Your wall mounted units are your most common. Air goes in the top, right here in this grill in the top, and comes out through the fins on the bottom. You usually have a minimum distance from this top of the unit to a ceiling because you need enough room for air to be sucked into the return. There are systems where that requirement is 2 inches. There are systems where that requirement is 8 or more inches. So it's a very important installation note. The other thing that's important about these wall units, especially if you're installing them, is to make sure you have the manufacturer required clearances on each side, because a lot of times you'll have to move components through the side of the system to get it out or something like that. So if you don't have the clearances that they tell you need on each side, you may not be able to service it without completely disconnecting it. Condensate pumps may be installed inside the unit or externally in some situations. Oftentimes this little reservoir is placed inside the unit, and then this, which is your actual pump, is placed outside the unit or in a ceiling. So this isn't your pump right here, right? This is just a reservoir. Some guys think that the pump is sitting inside the unit, but usually it's not. Usually these little mini split pumps, this is just a reservoir with a float switch. When the reservoir gets full, this pump comes on. And this pump can usually be so many inches, I think up to like 18 inches or something like that, above the reservoir. Ceiling mounted units are designed to fit a standard 24 by 24 ceiling tile opening. That is actually a load of shit. The newer units are often made to fit a 24 by 24 ceiling tile opening, but the older ones were often 30 by 30 or a little bit more. When they came out with these ceiling cassettes at first, none of these things were made to fit in a 24 by 24 tile. They just weren't. Who's that?
The ones that we're still putting in at the county,
Yeah,
they still don't fit 24 by 24.
yeah, I know. When I first saw the ceiling cassette, I was like, "Oh, that's the coolest thing in the world. That goes right in a ceiling tile, right?" Yeah, no. So most of them, except for the smallest BTU ones, your 6,000s or your 9,000, maybe even your 12,000 BTU units, those are the ones that'll fit in a 24 by 24 tile. Well, remember, we still have to move so much air, so you can only compact that space so much. So most of your ceiling cassettes do not fit in a standard 24 by 24 tile. And even if they have some that do, that may not mean the ones that you have do. I don't know why they put that in here, because that's one of those pet peeves. It's like, no, it doesn't fit there. It's a pain in the ass to get this thing in. I don't. The ceiling cassettes are okay, right? But it's probably my least favorite mini split design for a couple reasons, and none of them are a huge reason. It's not the end of the world. They're just so hard to service, and so much a pain in the ass to install because they don't fit in anything standard. And the condensate lines connect. I've never liked the way the condensate ceiling cassettes are. Just a pain all the way around. They can look pretty good sometimes, but they're a pain. Multiple indoor air handlers provide equipment style zoning without the use of duct or dampers. So this would be your multi-splits, or whatever you want to call them, where you have multiple line sets that go inside to each unit. So there'll be a manifold on the outside that hit multiple individual units from the manifold. But each one of these units still has its own line set, whereas in VRF, if you remember what we were talking about, the line set goes to a branch box first, and then they all go back to the unit. Those are two different kinds of setups, although these mini splits are starting to more and more resemble VRF. They've got a lot of mini splits now that are basically VRF style, where you can split the line set as you're going, but that's still a lot less common right now than the ones that have a manifold at the outdoor unit. Propose a system layout for your home. Consider the floor plan of your own residence. Make a sketch of the floor plan and show where you would place ductless indoor units. Note which style is shown on the plan: high sidewall, floor mounted, etc. Also indicate where you would place the outdoor unit. Some homes with floor plans may be best served by two separate systems. That's a pretty good exercise. Thinking about where you would place ductless systems. So a couple other notes I'll give you guys on ductless systems that you may want to consider. One, when you're thinking about where you would place them, you should very carefully look at the manufacturer data on how far it throws the air, right? Because you need it to cover a minimum amount of distance, say across a room. So if you've got a ductless wall-mounted unit in a room that's 20 foot long, so the air needs to move 20 feet to go from one side of the room to the other, you would want the throw on that system to be at least 10, but probably 15 to 20 feet, right? Because you want to be able to move the air from one side of the room to the other. Now, you don't want to do that directly. You don't want it to be too high of a velocity as it's doing it, but at the same time, you need to be capable of throwing the air that far. In houses where you're doing a lot of mini splits on a large footprint, a large floor plan, it can be very difficult at times to get enough flow that you're properly circulating the air. I'm actually helping install a system in a house like that right now, where we're throwing air one way to get to one side of the house, then trying to circulate it back and throw it the other way to keep the air moving. And then in some spots we're actually putting like little air shares, extra fans in to circulate the air in other rooms, so that we're moving enough air throughout the house, because that can be a very difficult thing to do with a mini split. Everybody sees these mini splits in relatively small spaces and they think, oh, this is the best thing in the world, right? You just have this one unit in the room and it does everything. But if you need to do that on a larger footprint, it's not going to be anywhere near as comfortable as a well-designed ducted system, right? Because you've got more places to move the air when you're running the duct. You've got more control over that. So that's one thing to note. The other problem that you run into mini splits a lot when people aren't thinking about the design is oversizing. Okay, and mini split manufacturers are doing a better job of designing around this problem, but often people will size these mini splits based on very, very inaccurate rules of thumb that they even put on the mini split websites and stuff. If you've got a 400 square foot room, then make it a 1-ton mini split or whatever the case may be. That's not a good thing to do. You should always do proper load calculations and proper sizing wherever possible where you install a mini split, because if it's constantly operating on too low of a speed, it's going to have trouble controlling humidity. And a lot of houses where there's a lot of mini splits that are oversized, people experience very significant humidity issues, because since they're variable speed, guys think, oh, it doesn't matter if I oversize it. But it does matter if you oversize them. It matters a lot, because a well-designed system controls humidity very well. An oversized system does not control humidity very well. And in general, you should err on the side of undersizing a system, not oversizing a system. If you're undersizing a little bit, you need to explain to the customer, hey, the system should be like 13,500 BTUs, but we're going to put in 12,000 BTUs, which means on a very hot day you may not be able to get it under 74 degrees or so, but usually as long as you're controlling humidity, that's relatively comfortable. You will be more comfortable doing that than oversizing this system by another quarter or half a ton, and it'll overall work better. So anyway, in general, I say never undersize, always oversize, because sometimes we overstate these humidity issues, but you definitely don't want to put in a 2-ton system where a half-ton or a 1-ton would have been fine, right? Oversizing it by that gross of an amount is a bad idea, except when you're doing all ductless mini splits and they also provide heat. You don't have any option but to oversize in those cases, but you want to do the best you can to keep it as small as possible still, and obviously recommend they run it in dry mode more often, or maybe even do a separate fresh air dehumidification system to overcome the humidity issues. But like I said, what you're going to see soon is a lot of mini splits that have more controls on them to control that humidity problem, but the humidity problem has been a relatively common occurrence with small houses and things like that that have been designed with all mini splits, because they tend to be grossly oversized. Any questions on any of that? All right. I'm gonna stand up for a second, stretch my legs. It'll only be 2 minutes, I swear. I'm gonna stand up for a minute, and then we will go over the next PowerPoint. Matter of fact, let me start it. Let me share it. There we go. And now we're going to talk about ductless and variable refrigerant flow systems, VRF, and talk about those a little bit more in depth. We'll go through this a little bit quicker because the last class we went over most of this, but if there's any interesting points that I see that we didn't talk about, we'll go over those. But give me just a second. Alright, so after we get done with this session, we should be able to do the following. Did I skip a slide? No. Identify ductless and variable refrigerant flow systems and describe the basic approach to troubleshooting. Describe the installation and troubleshooting of typical ductless. Identify and describe the operation of VRF, and describe the installation and troubleshooting of VRF systems. Related performance tasks are troubleshoot and repair a typical ductless or VRF system. Program the controller for a ductless or VRF system. Where deep snow is a common problem, mounting on the outside wall is an option. Code note: if a system is on the ground, it needs to be 3 inches above the ground. If it's mounted on the wall, it needs to be 6 inches above the ground. But if you have high snow in areas, it is definitely better to keep this, the higher the better, basically. That's why a lot of people use 3-inch pads with 6-inch pump ups these days. The higher you keep it above the snow, the better to keep the coil out of the snow in heating mode. Torpedo level is used to ensure the mounting plate is level. You want to make sure this mounting plate is level. If the mounting plate is not level, then the condensate pan is not level and it will not drain properly. If you need to err on one side or the other, obviously err on the side of it sloping more towards the drain, but you should keep it as dead level as humanly possible. A downward angle towards the outside wall is used when boring the hole to ensure water cannot enter easily. Anytime you're drilling from inside and outside, you should drill that hole at a slight downward angle going to the outside, and that is so water will not enter and drain to the inside of the house. That is a bad idea, and this is a pretty common sleeve used to penetrate the wall with a mini split. Remote controls. I hate these remote controls. I despise these remote controls. They look like they were made in 1982. I do not know why they cannot design a nicer looking remote control. Um, but yeah, these controls have lots of buttons, lots of bullcrap to them, and they just look dated. Very few mini splits have nice looking thermostats. Do not ask me why. There are some. They are getting more common, but they are not many. These controls, it is very important you read the instructions when programming these things because it is not very intuitive most of the time. Troubleshooting is looking at a chart, okay? Troubleshooting any mini split or VRF system is having the codes available and having the troubleshooting charts for those codes. It is absolutely imperative that you have that information. Um, I highly advise that if you're doing these systems to generally try and do the same brand all the time because it'll make your life a whole lot easier if you're going back behind your own installations. You want to be intimately familiar with the manufacturer that you use the most. It's not imperative. I mean, I don't even follow that advice. I install all kinds of different ones, but it is very beneficial for a company or an organization to try and keep these things the same so that their technicians are very familiar with the different codes that they have to deal with and very familiar with the troubleshooting process for these units. Often the problems you're going to have are bad temperature sensors or faulty circuit boards or refrigerant leaks on flare joints, things of that nature. You're going to have very few other more major problems, although you can have bad inverter compressors or bad inverter boards or whatever. But most often, your errors are going to be based on sensors and things of that nature, or poor installation. Poor installation is exacerbated on something like a VRF or a mini split. So, refrigerant leaks, especially because the line sets are small, can be hard to detect if you don't have a nice long test on them. Um, so it's kind of important to make sure you do your due diligence on testing and vacuuming the system properly. Um, but yeah, most of your troubleshooting is going to be learning how to retrieve a code, learning how to determine what that code is telling you, and learning how to troubleshoot that code. There's not much auxiliary troubleshooting you can do past that. The nice thing is it makes troubleshooting almost idiot proof as far as determining the issue. The downside is sometimes these codes have nothing to do with what the actual problem is, and you can think that you have a problem on the refrigerant circuit when really all you have is a bad sensor or something. And here's what your chart would often look like. These are just general, these don't go through codes, but it'll give you a symptom or a code, and then it'll tell you the items that you should check, and it'll tell you the details of how to check those items. And again, remember that this is not all encompassing, right? These people do not think of every absolute issue that could be related to the symptom or the code. Oftentimes they're generalized, but you have to learn to think a little bit, especially on the more difficult problems, on what other things might cause that same issue, and try and think of everything you can, especially again when it comes down to what if the sensor is actually bad. What if the fan motor is actually bad, you know what I mean? Something like that. Something that's more likely to fail than your circuit board, you know what I mean? Or more likely to fail than your refrigerant circuit or your expansion valve, things that really shouldn't fail. Again, more troubleshooting codes. This is what you'll be looking at. Issues like overcurrent detection, that can be a common nuisance trip. Things like compressor system sensor abnormality. What does that mean? It depends on the manufacturer. How do they determine that code? What sensors tell the board that that's what's wrong? Things of that nature. It's very important to understand, if at all possible, okay, what makes this system think that this is my problem? You know what I mean? What is an outdoor unit PCB abnormality? Is there a temperature sensor on the board that says the board's overheating? Is there a signal that should go from one terminal to another and it's not, so that it could be a bad electrical connector or something like that? Things like that, or you have to start thinking outside the box when it comes to these complex circuits, because you're looking for an issue that could just be a bad connection. You're looking for an issue that could be a broken wire, and things like that. Especially the broken wires and all that are ones that you want to always keep in your head. What if it's not getting the signal back from the sensor? It says the sensor's failed, but what if the problem is the connection and not the sensor itself? Test the sensor. Make sure that's the problem. Things like that. So here it's giving you some charts for a four-way valve abnormality, and it tells you the room temperature thermistor and the indoor heat exchanger thermistor are checked if they function within their normal ranges in each operation mode, right? So if they are not in their normal ranges, it might throw a four-way valve abnormality. And on something like this, I could imagine low airflow might cause a similar problem, right? If the heat exchanger and the indoor temps are not in their normal operating ranges, but the system's freezing up, it may tell you have a four-way valve abnormality where you just have an extremely dirty filter or something. I don't know for sure that could be it, but it could, just looking at this troubleshooting chart, that could be something else I might be looking for. Following condition continues over 1 to 10 minutes after operating for 5 to 10 minutes. So this is how the malfunction decision occurs, right? So if any of these conditions continues for more than 1 to 10 minutes after the system has been operating for at least 5 to 10 minutes, so it should have reached, its normal operating condition by that point, the cooling dry room thermistor temp minus the heat exchanger temp is less than 5 degrees difference, or 5 degrees Celsius, or 9 degrees Fahrenheit difference. So if they are very close to the same temperature, then it'll give you that error. And heating, if the indoor exchange temperature and the room thermistor temperature is again less than 9 degrees Fahrenheit. If the error repeats, the system is shut down. Reset condition is continuous run for about 60 minutes without any other error. So it has to have no other errors for 60 minutes, and then it can reset. Supposed causes: disconnection of a four-way valve, defective four-way valve, defective outdoor PCB, defective thermistor, refrigerant shortage, water mixed in refrigerant, defective stop valve. Obviously, if I'm looking at an issue like this, the first thing I'm going to be checking for is defective thermistors. The next thing I'm going to be checking for is low on refrigerant. After that, I'll start checking all this other stuff, and if there's anything I can check while I'm looking at those two issues, I will. But you kind of pick the ones that are most likely to be your problem first. Things that are most likely to fail, or things that will occur due to a poor installation, are the first things I look for, and then more robust or complicated components come next. Obviously, the last thing that I would condemn is the PCB, because you need to make sure everything else is good before you can start condemning a circuit board, right? And then here's a flow chart. So these are nice, especially if they're made well by the manufacturer. If the four-way valve is the four-way valve disconnected? Yes, connect it. If it's not disconnected, is the harness out of the connector? If yes, then reconnect the harness. If no, check the continuity of the four-way valve coil in the harness. Disconnect the harness from the connector. Resistance in the harness is between harnesses about 1,000 to 2,000 watts. What? See, that's what I'm saying. I don't know what that means. That's what I'm saying. If they're made well, right? I don't know what that means. Resistance, I assume it's supposed to be ohms, but 1,000 to 2,000 ohms would be a lot. So I don't know what they're saying there. Who knows? Anyway, check number 13. Check the four-way valve switching output. If not, replace the outdoor unit PCB. Are the any thermistors disconnected? Yes, reconnect them, so on and so forth, right? Just follow the chart, check everything you can. Worst case scenario, call the manufacturer if you get to a point where you're stuck. Sometimes they have better charts than they give you, or they've seen issues that they can help you with. You know what I mean? Oh, often we have this thing that's the problem, so check that first. Unlike typical ductless systems, all indoor units are connected along a single refrigerant piping circuit. Now we're talking VRF. So VRF will have a single piping circuit with multiple branches. This would be a heat pump VRF, the way it looks to me. So this whole system would be in either heating or cooling, and we have multiple connections along a single main line set. Here we're showing engineered branch connections. So this could be a 3-pipe system. It may or may not be, but it kind of looks like a 3-pipe system because they have the branch boxes. And then of course these could be heating or cooling, like we were talking about last class. They can run simultaneous heating and cooling. Here are some pictures of, this is obviously, I call these Daikin style because this looks a lot like a Daikin branch connection. And then I've never used these headers, but they've been around for a long time too. Another note on these connectors, I don't know if we discussed last class, is you see how the piping is a size and then it goes up and then steps down and steps down. This is the only time where that's super acceptable in refrigeration. Sometimes your vertical piping is sized different than your horizontal piping in refrigeration, but all these up and down, sometimes you have another reducer that goes back up to another size at the end or something. Don't get too concerned about how pipe gets from A to B to C size or whatever. Reducing and increasing is pretty common on these branch connections, and it's not something to be worried about too much. Just don't do it anywhere else in your line. Proper distances between fittings are crucial. We talked about that. At least 20 inches. Again, our rule of thumb is usually 2 feet. Between branches or the branch selectors, our rule is usually 4 feet. At least 20 inches after a branch connector before a turn. All of these are to A, minimize noise as the refrigerant is flowing through the system, and B, to provide good airflow, good refrigerant flow between these branches. You don't want these lines to be splitting and turning a lot in short distances because the turbulence could cause the refrigerant to have trouble traveling where you want it to. Branch selector boxes are used in heat recovery systems. Remember that? So heat recovery systems, the branch selectors, they're back in.
Okay, never mind. I was thinking, what was there?
I don't know. Double check, but I'm pretty sure she's in here. Anyway, branch selectors are going to switch between heating and cooling at individual zones or units, but each individual zone with a branch selector can operate in heating or cooling at any given time. This is a Daikin setup. I can already tell you that by looking at it. This is exactly how the Daikin wiring goes. So the common terminal labels make wiring simple. Everything is 2-wire from one thing to another. So you have 2 wires going to your remote control. You have 2 wires going to your next unit. You have 2 wires, T1, T2, that's forced off. That goes to a safety. But these go unit to unit, and then you also have to indoor unit to outdoor unit to your next selector over here. I forget. Indoor unit goes to your indoor. F2 goes to your outdoor, and then Q1, Q2. I can't even remember these well enough to tell you. It's been a while since I've done a Daikin system that had branch selectors on it. It's been a good few years now. But anyway, it's basically 2-wire daisy chain to everything. Your branch selectors communicate to your indoor units, which is always the case for the most part. Your indoor units a lot of times are connected to your thermostat, but some systems, different manufacturers, I think the thermostat goes to the branch selector itself. and then you daisy chain the branch selectors, and that one of those goes back to the outdoor unit. It's 2-wire to everything. It's pretty simple once you've learned it. Communication wiring must form a daisy chain. The star connection shown will not function properly. So you go from one unit to the next unit to the next unit. You do this with all your branches, then you do that with all your indoor units after your branch, and you do that back to your outdoor unit. Everything has to be a daisy chain. You cannot connect one box to multiple units, right? So if these were indoor units and this was a branch selector, you can't go from the branch selector to each individual unit. That's not how it goes. It goes to the first unit, then to the next unit, then to the next unit. And again, I was telling you the best way to think about that is just picture that this branch selector knows which unit it's talking to by how much the resistance of the wiring is. So if it's getting miscommunication, really it pings it back and forth. It doesn't matter. To me, it's easier to think about it as wiring resistance, because that helps you remember why you can't make poor wiring connections as well, because it tells how long it takes for that communication to go back and forth by the resistance of the wire. And so if you've got a star connection like this, these two wires might be the same resistance, right? And if they're the same resistance, then it's not going to know which unit it's talking to. So we daisy chain them all, so we know for sure, it's 2 ohms to get to unit 1, then it's 4 ohms to get to unit 2, then it's 6 ohms to get to unit 3, and so on and so forth. The time it takes that signal to go back and forth, or how much resistance there is in that signal, is what determines whether or not they can communicate. So that picture in my head is what has always helped me kind of remember a lot of the rules associated with these things. VRF troubleshooting is the same thing. Troubleshooting charts, and actually when it comes to VRF, a lot of it is have the computer, have the software, have all the proper training. If you're troubleshooting VRF, you should be trained in that manufacturer. You should only be doing very, very limited troubleshooting, and if you have not taken the manufacturer's courses on troubleshooting them. It doesn't mean you can't go out and diagnose a bad condensate pump. You can probably pull that off if you're a pretty savvy technician, but you don't want to be going out there diagnosing complicated problems without having the requisite training to do it. VRF troubleshooting is about taking the troubleshooting class for that manufacturer 100%. That's the most important thing. I'm not even going to go through these charts with you, because they don't really matter. I'm telling you, if you want to troubleshoot these things, take the class on it. You take the installer class, then you take the commissioning class, then you take the service class. They'll cost they'll cost $400 to $800 each class, but by the time you're done, you'll be one of the only guys around that can troubleshoot them properly. So it's a good thing to do, especially if you're doing a manufacturer where there's not a lot of technicians for that manufacturer in the area. It is very worth your while to take the VRF classes on troubleshooting them, because there can be a lot of troubleshooting on them. Yeah, it can get real bad, especially if there's a poor installation. But it doesn't even have to be a poor installation sometimes. Sometimes they're just riddled with a little problem, and a little problem on a VRF can turn into a big problem for a while until you figure out what that one problem that caused all the problems is, if that makes sense. Special equipment may be available that acts as an interface between the system network and a computer. And that is a very important thing to have, so that you can see what the system is doing. Why do liquid line headers allow refrigerant to exit from the bottom while the suction line headers do not? The liquid is influenced more by gravity, right? We talked about this a little bit. Having the lines connect at the bottom provides some insurance that any vapor that may form in the liquid line is unlikely to enter the lines leaving the header. So since liquid is more effective by gravity than vapor, we can run liquid line headers, those straight bar manifold style headers, straight down, or I think they still allow them straight to the side too. But anyway, you can run those, whereas they will not function very well on a suction line. So it's less common to have that kind of piping arrangement approved by a manufacturer on a suction line. Why do VRF heat recovery systems require 2 refrigerant lines instead of 3? Or sorry, 3 refrigerant lines instead of 2. Because VRF heat recovery systems can provide heating and cooling at the same time. Therefore, a separate hot gas line is needed to provide heat while other units are operating in the cooling mode. Remember, your 3 pipes are liquid line, suction line, and hot gas. No, not hot gas. High pressure, low pressure gas. Remember, your 3rd line could be suction and it could be discharge. It's usually discharge gas in that 3rd middle size line, but it could be suction as well on very hot days where everything's calling for cooling. And then there's your performance tasks. All right. Alright, we lost Tyler. Computer shut off. Alright, let me respond to him real quick, I guess. Alright, let me take a look at the test. This looks like a really easy test too. I already looked at it a little bit. It's a pretty short test. So on zoning, ductless, and VRF systems, you'll want to remember the function of the master thermostat in a zone system. Alright? So remember, on older systems, the master thermostat is the only thing that can control system operation, right? Most zone systems... So again, remember the function of the master thermostat in the zone system. It controls system operation in older systems. Is a zone damper normally open or normally closed? That's important. A standard 2-wire zone damper. Is it normally open or normally closed? What is that? Okay. Look in your book. Try and look in your book and see what it says, because I don't think we discussed it too much. This is probably one I'll let you guys try and figure out. When a zone thermostat fan control is switched from auto to on, what should happen? See if you can find the answer to that. When a zone thermostat fan control switch is moved from auto to on, what should happen with the zone dampers? See if you guys can find the answer to that. It should be relatively intuitive, but... Alright, what control stages in a zoning system? Is it time? Is it temperature? Is it liquid line temperature? What controls multiple stages of cooling in a zoning system? We talked about that. So remember how that is. Which of the following approaches to handling bypass air offers the best performance in commercial applications? Remember what let me make sure their answer is the same as mine. Ooh, maybe not. Okay, so the answer is going to be what we looked at on the VVT system, okay? What we looked at on the VVT system, how they controlled the bypass air, that's going to be what they consider the best in commercial systems. Alright, so how was the VVT system we looked at? How did the bypass air go on that? Remember we talked about shielded wiring. On VRF systems, It's not very common for it to be shielded, although some manufacturers like Carrier do require shielded wire. But on the VVT system, what kind of wire did they have? Make sure this one's the what I think it'd be. I mean, it should be. Alright, so we didn't talk about this, so let's discuss it real quick. The blower wheels and those mini splits, remember I told you the access for them is important, especially on each side, because some of those things you have to remove. Part of that is on certain mini splits, the only way to get the blower wheel out is through the side. A lot of them it can come straight out, but not all of them. It depends on the design of the mini split. So that's why you need that side clearance oftentimes, so you can actually get that blower wheel out, because that blower wheel is a very long, very slender blower wheel. Okay, so it's got to move all the way out of side, and I've had some that were like that, where you have to slide the whole thing out in one direction. And if you don't have proper clearances on either side, that's gonna be difficult, if not impossible, without actually removing the unit. So most of the blower wheels on those ductless indoor units are long, slender, standard centrifugal blower wheels. Okay, if you've never seen one, it's basically just it's like a long tube of a squirrel cage. Remember, most ductless systems, alright, where's their expansion valve located? On a VRF system, the expansion valve is always still located on your indoor unit. But on the ductless system, it is often not. VRF systems, what can they do that a standard mini split system can't, right? Because you have 3 pipes. What can they do that a standard mini split system cannot? Remember, you have to have 3 pipes for that, though. A heat pump VRF cannot do the same thing a heat recovery VRF can. Heat pump is a 2-pipe system. Heat recovery is a 3-pipe system. And we talked about it last class, but I'll reiterate it here. If you're charging any of these systems, alright, if you're charging any of these systems, mini splits, VRF, newer systems with microchannel coils, I recommend you always charge systems by weight. It's imperative. You have no other choice on VRF or mini splits, really. If you're doing it properly, you have no choice but to weigh it in. But I'm telling you, as a rule of thumb, if you get good at always weighing in your charge, there's really no reason to fret too much about anything else. That doesn't mean you shouldn't be looking for system issues after you've weighed a charge in, but it does mean that once you've weighed the charge in, as long as you've accurately calculated what your charge should be, you already know the system charge is good if you weighed it in properly. So it completely eliminates a whole problem of undercharge or overcharge. Alright, completely eliminates that out of the equation. So anytime you're able to weigh a charge in, just weigh the charge in. It's not that difficult. Even if you got to pull some charge out to weigh it back in, if you've got even halfway decent recovery equipment, that is not a difficult task. Okay? The most important thing, the hardest thing to get out of that is a good, clean, vacuum down recovery cylinder. As long as you got that, and a decent, even the cheap recovery units these days usually do a decent enough job for you to pull most of the charge out so that you can weigh it back in. Usually, no matter what you're working on, except on critical charge systems like small mini splits or systems with microchannel coils, a couple ounces here and there aren't going to kill you. As long as you pull the majority of the charge out, pretty much all of it, just leave a few psi in there basically, then you can weigh it all back in quite easily, be extremely accurate, and not have any issues. Or if you do have issues, you can look somewhere besides the charge, because it's obviously not your charge at that point if you accurately weighed it in.